Okay, so this particular lesson's on uniform circular motion. We will need to look at what is circular motion. Just pick it up from GCSE really. Then we're going to look at what we mean by radians, or what are radians, and then this concept of angular speed and angular displacement. So what is circular motion? How do you recognise it? It's not particularly difficult to understand. This is circular motion. It's when something's moving in a circle. Uniform circular motion is when the object moving in a circle is moving at a steady rate. Now we need to talk a little bit about speed. What do we mean by speed when I say a steady rate? Well, if you imagine the velocity of the blue dot, the velocity of the blue dot is constantly changing even though the speed is constant. The speed is the magnitude of the velocity, and that is not changing. But remember, velocity includes direction, so that blue dot is changing direction constantly, so therefore the velocity of that blue dot is changing constantly. So the first little idea in circular motion you've got to remember is that even though it's going round at a constant speed, its velocity is changing. And this, when we look in the next lesson, when we talk about the idea of acceleration, this helps us to understand why the object is accelerating. So this is circular motion. It's accelerating towards the centre. Its velocity is at a tangent to the circle. Its velocity is constantly changing, but the linear speed, or the speed of the blue dot, is constant. So to describe circular motion, we need this idea of radians. Now, angles may always have been measured in degrees from your point of view, but in physics we often measure angles in the units of radians. Just to, in case you've forgot or can't remember or need some revision on radians, just sort of break it down. The circumference of a circle, you know, is pi times the diameter, which is 2 pi times the radius. And the frequency is 1 over the time period, so f equals 1 over t. If you look at the linear speed at any point on the perimeter, remember it's going at a constant speed, so to work out that constant speed we do a speed equals displacement over time, and you can see here that our displacement is 2 pi r, which is the circumference, divided by big T, which is the time period. So what do we mean by a radian? Well, this is the radian. It's always used in circular motion, not degrees. And to get an idea of what a radian means, a complete circle is 2 pi radians. So 360 degrees is 2 pi radians. Where does that come from? Well, this is the nicest diagram to look at. A radian is when the radius length, so these are 2 radius, that is also equal to the arc length. So when that distance is a radius, obviously, that distance is a radius, and this distance is a radius, this angle here is called a radian. From that, you'll be able to see that there are 2 pi radians in a circle, because there are 2 pi radiuses in a circumference. This little diagram is showing you that if we divided it all up and we did that picture again and again, you'd have 1, 2, 3, 4, 5, 6 and a bit. 6 and a bit radians in a circle, actually 6.28, which is 2 pi, 2 times 3.14. There's some of your conversions. If you did work it out, 1 radian is about 57 degrees, 2 pi radians are 360 degrees, pi radians are 180 degrees. So pi over 2 radians is 90 degrees. Okay, let's talk a little bit about what we mean by angular speed and angular displacement. We've talked about linear speed, which is sort of the speed of the blue dot, if you like, going around the edge of the circle. But now we need to define its speed in how many angles per second, or if you like, rather than how many meters per second. Okay, so angular speed is this. It's similar to the normal speed equation, but instead of the distance divided by time, or displacements divided by time, it's the angle turned through in radians divided by the time taken. So again, let's put in some stuff that we know. If we know that for one time period, one time period t, that's 1 revolution, we know that the angle that's been turned through is 2 pi, because we've already defined that, and we know that in 1 revolution the time taken is the big T, which big T is time period. So omega, which is the symbol for angular speed, it becomes equal to 2 pi over t. Because frequency is 1 over the time period, it's easy to write this equation as omega equals 2 pi f, which the units of that are radians per second, which is quite easy to see from this formula here. Angular displacement is kind of like the total distance travelled if you're talking about linear speed. So linear speed is how fast you're going at any one point. Linear displacement would be how many metres you have travelled in total. Well, angular displacement is how many angles, if you like, or your angular speed times time. So it's quite literally, it's how many radians you've passed through. We get this by multiplying the angular speed by the time. So we get a formula of 2 pi f, which is angular speed, multiplied by t, and that will be measured in radians. We've now got a formula, or a couple of formulas for radians. It would be very nice if we could link angular speed omega with linear speed v. So let's see if we can try and do that. So we talked on the previous slide that linear speed v is equal to displacement divided by time. So displacement divided by time, if we're going in a circle, we know that in one time period, big T, the total displacement is 2 pi r. That's all the way around the circle. So linear speed is 2 pi r over t. From what we can see above, we can see that omega is equal to 2 pi over t. So in this formula here, if I just insert omega as 2 pi over t, then I easily can see it's the v becomes equal to omega multiplied by r. And on the formula sheet, you're given this just rearranged to give you omega equals v over r. That's quite an important formula, which you'll be using in the questions. So we've sort of built up two formulas. The first links angular speed with the frequency, and the second links angular speed with linear speed involving the radius. Let's do a couple of quick questions. An electric motor turns at a frequency of 50 Hertz. Calculate its time period and the angle it turns through in radians in 1 millisecond and 1 second. So dead easy, first of all. We know the formula for time period is 1 over the frequency. 1 over 50 is 0.02. Written that in seconds would be 20 milliseconds. Now, the second part's a little bit more complicated. In 1 millisecond, we need to work out how many turns it goes through. Now, you know that the time period is only 20 milliseconds. So in 1 millisecond, it hasn't gone through a complete turn, far from it. It's only gone through a 20th of a turn because the time period is 20 milliseconds. So a 20th of a turn will be a 20th of a circle. And remember, there are 2 pi radians. So if we do a 20th of 2 pi radians, 20th of 2 pi radians becomes equal to about 0.31 radians. Same principle to work out the angle it's turned through in 1 second. In 1 second, it has gone round more than once because the time period is 20 milliseconds. So if we say how many 20 milliseconds are there in 1 second, that's 50. So it's done 50 complete turns. So again, each complete turn is 2 pi radians. So if we go 50 multiplied by 2 pi gives us 314 radians. Okay, another question. A stirrer in a food mixer rotates so that the end of it is moving round once in 0.07 seconds. If the length of this stirrer arm is 9 centimetres, calculate the linear velocity at the end of the arm, the linear velocity halfway along the arm, the angular velocity of the arm, and the number of revolutions per second, which is the frequency. Okay, if you just look at letter A first, the linear velocity, it's a straight calculation of the circumference divided by the time it takes. We know the circumference of this circle is 2 pi r, which is 2 pi times 0.09. The stirrer arm is the radius. And we divide that by the time it takes, which is 0.07 for 1 revolution. We get an answer of about 8.08 metres per second. The linear velocity of halfway along the arm, exactly the same, apart from I'm not using 0.09, I'm going 2 pi times 0.045. Divided that by the time period, I obviously get half the speed. So you're moving at half the speed as you move down the radius by half. Angular velocity from our formula is 2 pi divided by, well, I've used 2 pi f instead of f, I'm just using 2 pi over t. So 2 pi divided by the time period gives me 89.8 radians per second. And finally, it's just asked me to work out the frequency. That's easy, 1 over the time period, 1 divided by 0.07, which is 14.3 hertz.